Hello, everyone, and welcome back for another lesson, virtual style. So this is where we're at. It's 144. How does velocity change? Now, just to recap where we're at, building up to this point, because I want you to know where it comes from and where we're heading, so it's all connected, right? Because math really is all connected. Now, we've looked at position graphs, sometimes also referred to as like distance graphs, even though I don't really like that word distance, which you'll see in this lesson. Was it the last lesson? I forget. And if you see a position graph, so we'll call this miles per hour, where this right here represents a position. What we know about the graph, and that's just a arbitrary graph, you can draw anything. What we know is that the velocity is the slope of this graph. It's how its rate of change, right? So at that point, whatever point that is, you would say that that's the velocity at that particular time, right? Same thing down here. If you found the slope at this point, that would be the velocity at that particular time, at that particular hour. So we've learned that. And then we started looking at velocity graphs. So I'll make another velocity graph here. And we'll call this miles per hour, because now this is a rate, which makes it a velocity graph, and then we'll call this per hours. And again, it will be some arbitrary graph, like so. All right. And what we should know about velocity graphs is where we're at, is that we know that the area under the curve is the displacement. Now, that's a new word, and that's because we're getting to what it truly means now and not just beginning to understand. So we often use the word distance when we first teach this, but the truth is that the area under a curve is displacement, not distance. And the reason for that is because distance is equal to the absolute value of displacement. Distance is usually only referred to as a positive number. But when we talk about motion, sometimes you can go forward and back, and your final position ends up behind you, in which your displacement is a very small amount. Like you might walk forward and back a lot and then end up just 1 foot behind you. Where your displacement would just be 1, but the distance you traveled is a very large number because you're traveling a lot. In fact, to help you kind of visualize this right here, the area under the curve would be displacement. This graph right here, if it looked something like this, this would be what this graph would look like. This would be what the graph would look like if the distance was to equal the displacement here, because it's all positive already, meaning that when your velocity, you're staying positive, you're only moving away. So your final position of where you end up, if you're only moving away from your starting position, will be the same as the distance you traveled. You never end up going backwards, in which displacement you'd have to subtract out from your math, while distance you just keep adding that on. And furthermore, that's distance and displacement. If we're looking at a velocity graph, what we also know is that the area under the curve is displacement. Area under the curve here would be miles, right? And we've talked about that because if you did area under the curve, length times width, you would make a rectangle. Miles per hour times hours would just net miles. But the question that we're getting to today, despite all this work, is how does velocity change? So what does the slope on velocity mean, right? What does the slope on velocity mean? Right? So at this particular time, which we'll call c, whatever value that is, at that particular hour, how is the velocity changing? Right? And notice that rate of change would be miles per hour. You want to know how is the velocity changing per hour. And that's the unit there, the miles per hour. That's what we want to look at. All right. And that's velocity right there. And I put in the change in to just help you see it. It's like the change of y over change in x, but I'm throwing units in there. All right. Now, in fact, the slope velocity, how velocity is changing, we call that the acceleration. And that is a big word that you'll be seeing all year long, kind of the third big key. Right, so we'll define that down below, look at examples, and hopefully help clear this up a little bit. So acceleration is the rewrite this. Acceleration defines how the velocity is changing. Right. You can refer to it as like the rate of change of velocity. Graphically, that's the slope on a velocity graph. And I like to star that one because we often look at a lot of graphs in this class, and it's important you know that. So that slope right there, that's a acceleration. And you can see that that's a positive acceleration, so his velocity is changing in a positive manner. And then if we were to look at like that point, we'll look at more examples. Right, the velocity is still positive because we're in the positive y values, but the acceleration is negative, which we'll talk about what that means. If you have a positive velocity and acceleration is negative, what's really happening? So let's look at some examples down below of velocity graphs and understanding acceleration. Right. So example 1, let's look at a velocity graph. So this will be a v of t graph, and we'll just put it in meters per second. And this is seconds. And the first one I will draw like this. So there's a random graph, a velocity graph on v of t. Now, a few points, and we'll label these points, say A, B, C, D, E, F, and G. And this is a problem similar. I'm going to kind of word it differently in what makes sense to me. You want to make it make sense to you as well. I'm going to put a point G and actually call this H. I'm sorry. All right, so let's just go through what's happening at all these points. So at A, what's happening here? Now, something to keep in mind is this is a velocity graph. So every point that's up here has a positive velocity because these are the positive y values. So every point in this whole region above the x-axis, v of t, your velocity graph, is positive. Just like any point down here, your velocity is negative because it's below the x-axis. Its outputs, its y values are negative. And then the x-axis here is when v of t equals 0. Your velocity is 0, meaning you're standing still. So at point A, what's happening? Well, we're in the positive velocity, so that's a positive velocity. And the slope is positive, so that also means you have a positive acceleration. So what you might think about to make sense of that is positive velocity means you're moving away. You're moving away. And the positive acceleration means that you're speeding up. Right, so you're continuing to move away and you're speeding up. If you can picture what's happening at point A. At point B, what's happening here? At point B, we're at the top here, And notice that if we were to find the slope here, it's 0. So then notice, but the velocity, that point is still in the positive part of the graph. So you still have a positive velocity, but now your acceleration is 0. Right? You're not moving. So what's happening? So if you have a positive velocity, that means you're still moving away from your starting position. And acceleration of 0 means that you're moving at a constant speed. Because remember that acceleration is the change in velocity. So if there's no change in velocity, it means that you're staying at the same velocity. You're not getting faster, you're not getting slower, you're just staying at the same speed. All right? Point C here. I'll make a little mini slope on that. You have a positive velocity, it's still in the positive part of the graph. I'm just going to start using V to save some writing. Not necessarily the best practice. And then now the acceleration, A of t, is negative. Definitely better to use V of t and A of t. So positive velocity, acceleration is negative. So that means that we are moving away, and acceleration is negative. That means your change is, if you have a negative acceleration, what's happening is that you are slowing down. Right. At point D here, we're on the x-axis, so now your velocity is 0. And your acceleration is still negative here though, right? So the acceleration is still negative. And I'm going to start using inequalities because this is more how you need to start describing it. The words I start with, but really that's notation that we're going to be using in the future. So we're going to start tending towards that way, but I'll try to still say it. So velocity of 0, acceleration is negative. So what's happening there? If you have a velocity of 0, that means that you've stopped, right? You're not moving. And acceleration of 0 means that you are, how can I say it? It's basically like you just, slowed down to rest. And let's go to point E. And we're going to keep going because I don't want to confuse you. And maybe if we keep going, this will make more sense. All right. At point E, now we have a negative velocity. And your acceleration is also negative. So what's happening here is now you're moving backwards. Or you can imagine in this bomb, we were moving away this whole time. We stopped. So it's almost like since we are now moving backwards at that point, we actually turned around because of turned around. So now we're moving backwards or back to the starting point. And your acceleration is negative. Now, acceleration negative doesn't always mean necessarily slowing down here. This one right here, your acceleration is speeding up. Right? Your acceleration is negative. That's still true, but you're speeding up because you're moving backwards at a faster rate. Right? At point F, now we have a negative velocity, and acceleration is equal to 0. So that means that we're moving backwards at a constant rate. And that's why the acceleration is 0, because it's constant. Point G, we have a negative velocity and a positive acceleration. So in this case, that would mean that we are still moving backwards, because it's a negative velocity. But an acceleration of positive here means that we are how can I say it? Your rate of change is positive. You have a negative. If you're moving backwards, you actually are heading back to your in this case, you're slowing down. I'll put it that way, and I'll explain that. Because if you're moving backwards towards your original start, towards a zero velocity where you just stand still, that would mean that you're slowing down. Well, in this one over here at point E, you're moving backwards, but you're moving away from rest, and that's why you might say back in E you're speeding up. Even though it gets kind of confusing with acceleration's negative, that doesn't always mean that you are slowing down or speeding up. It's kind of in the context of what's also happening with velocity. All right. And then the very last one, H. At point H, your velocity is 0. And we're going to assume, but we don't really know, that the acceleration is positive here. So that means that you are standing still. You're not moving if your velocity is 0. But acceleration is positive means that in this case you slowed down as well to H to get there. Now, I don't know if that makes sense, so we'll keep going. And it's very possible I made a mistake here. So if I did, definitely message me or email me, and I'll put it in the comments that there's a mistake in my video, because I think it's all right. Pretty sure it's right, but sometimes I do make mistakes on these types of problems. Okay, so let's go to the back, look at a few more examples. Let's see here, example 2. And remember, these are all velocity graphs. This one will do meters per second and seconds again. And let's say we look at a graph now that looks something like this. We go up, over, down, over, and back, up. Right, so this represents a velocity graph right here. Okay. And then I'll mark some points to talk about so we can kind of make sense of what's happening here. Let's go right here. Let's go right here. And length there, A through G. Okay. So if you want to, maybe stop the video, see what you get for A through G here, and then compare with what I get and see if you are on the same page with me as we go through this. So at A, you have a positive velocity and a positive acceleration because the slope is positive. That means that we are moving away and speeding up. Okay. At point B, you have a velocity that's still positive, but your acceleration is 0. So at that case, that means that you're moving away still because you still have a positive velocity, but at a constant rate. You're not speeding up nor slowing down. At point C, you have a positive velocity, but your acceleration is negative. So in this case, we're moving away, but we are slowing down. All right. Because we're getting closer to 0, and 0 is, on the velocity graph, that's a point of rest where you stop moving. Okay. At point D, velocity equals 0, acceleration is less than 0. So at that point, we are standing still because we're not moving. All right. Now, what's interesting about point D is leading up to point D, we have a negative acceleration, meaning that we're slowing down. But notice, as soon as we have a negative velocity, we start speeding up, because if you slow down to stop, in order to keep moving in, you have to have a positive acceleration to get from a point of rest to a point of movement. All right. So that's something a little bit extra. So you could say, right before you're slowing down, but right after, you have to speed up. At point E, our velocity is now negative, and acceleration is 0. So that means that we're moving away, or backward, not away, moving backwards, and at a constant rate. Point F, we have velocity is equal to 0, and your acceleration is greater than 0. It's positive, right? Slope is positive there. So at that point, that means that you're standing still. But kind of what's happening, same thing up here in D, is right before this point, we're moving backwards, but we're slowing down to a stop. And then notice that we're going to switch directions here to move forwards. So then we're going to have to speed up. So at this point, we're going from slowing down to speeding up, which is kind of similar to what's happening before because we're changing, the velocity is changing signs here. And at point G, you have velocity is positive and your acceleration is positive. So that means that you're moving away again, whatever that away looks like, and you're speeding up. Now a table in case that might help you see this if we compare the two. So let's look at how velocity, okay, so let's go velocity, acceleration, and what's happening. This will be the last part of this video. And then you just have to try yourself and make sense of it, make mistakes. If you make mistakes and learn from it, that's kind of how this is. Especially if you haven't taken physics before, this might be new to you, and it gets tricky to wrap your head around. Even me, when I do these, I have to wrap my head around it. So velocity is positive and acceleration is positive. That would mean that you're speeding up, right? Because velocity positive would be like this point on the graph at point A, where you're moving away. You have a positive velocity, so you're going from like 10 miles per hour up to 20 miles per hour. So you're moving away from your start, being positive, but your acceleration is increasing. You're speeding up, right? If you have a positive velocity and a negative acceleration, you are slowing down. And I'll say like it's like a point A on that graph above. This would be like point C. And the reason there is you're still positive because we're in the positive part of the quadrant. All of this up here, V of t is positive. All of this down here, V of t is negative. So we're still moving away with a positive velocity, but we're approaching a resting point. So that would mean we're slowing down, right? Because if you're moving away but approaching a rest, you are going to slow down. Now I'm going to add a point here. We'll call that point H really quickly. Up at the next one. If you have a negative velocity and a negative acceleration, such as point H here, negative velocity and your acceleration is negative, you are speeding up. And if you look at point H, at point D, we're at rest. So if you want to start moving backwards, in order to go from rest to moving backwards, you have to speed up. Your change of velocity is going to, it's like physics. You have to move quickly to get out of your resting position. Right? And then the last situation that can happen is if you have a negative velocity and a positive acceleration, such as point, I'll add a point here called point I, that would mean that you're also slowing down. In which case, if you look here, you're moving backwards at point I with the negative velocity, but we're approaching rest, in which case that would mean that we're slowing down. So hopefully this table is a nice summary of all of this. There's a little trick here if you notice. If they're both the same, it's like multiplying. You get speeding up and speeding up, where speeding up sometimes you associate with positive. And if they're opposites, you're slowing down. It definitely helps to visualize it for me. For me, it helps. It helps to visualize a velocity graph and picture, the slopes. And am I getting closer to zero or not? And that's how I've learned it. That's how it makes sense to me. Maybe you have a different approach, especially if you're taking physics. I'd love to hear it. And I'm sure your classmates would appreciate it too if you have another way of knowing these. So there it is. That is talking about acceleration and understanding graphs. Definitely give it your best attempt at the beginning. In my experience of doing this myself and of helping people in tutorials, it's a little bit tricky. All right. Good luck on this assignment.